And then at the end, I'm just going to show you a little bit of pilot data that we just started collecting, which might suggest that that solution might work. Okay, so over the past few decades, what's happened in cognitive neuroscience is that we've developed a whole suite of experimental paradigms that describe in exquisite detail how we might go about making decisions and seeking out rewards in the world. So some of these paradigms, for example, look at how we learn from reinforcement about which behaviors are likely to lead to rewarding outcomes. Some of them look at how we sample and check for information when we're trying to make a decision. And some of them look at how we might weigh evidence across time when trying to make a simple choice and integrate that external evidence with our prior beliefs. And for each of these tasks, what cognitive neuroscience has provided us with is ways of describing specific aspects of behavior in each of these tasks with well-defined and parameterized computational models. And this means that if we change one parameter in the model, we know exactly what this means for how subjects' behavior should change. What's also true for each of these tasks is that we now have a good understanding of their neural basis, so we know which brain regions are involved, and we're beginning to understand how those brain regions contribute to these tasks. And more recently, what's been found, and this includes some work here from Mike Browning here in our own department, is that across a number of different mental health conditions, it's been possible to identify certain aspects of behavior that are captured by those computational models that appear different in people who are experiencing those conditions. And this is what's often being referred to when people are talking about this kind of new field of computational psychiatry. So let me just zoom in and show you one example of a task where the neural mechanisms have been very clearly delineated. This is a task that's been widely studied in cognitive neuroscience, and what subjects have to do is they have to look at a cloud of dots that are kind of moving in random directions and report whether the dots on average are moving to the left or moving to the right. And this seems like a really simple task, but what it allows us to do as experimenters is by manipulating the degree of coherence, the number of dots that are moving coherently in the stimulus, we can control very precisely the amount of evidence that supports one conclusion or another. And what this means is that we can then measure exactly how much information people are weighing from a stimulus across time and integrating that with their prior beliefs. And what's also been discovered is that there are neural signatures of this process of evidence integration across time. And these have been extremely well characterized in neural data, originally recorded from animal models, starting with macaque monkeys and more recently in rodents. But importantly, equivalent signatures of that process have recently been identified in human imaging data, such as EEG. So we think that these EEG signals might allow us to measure how participants are weighing external sensory evidence with their current beliefs in order to form a simple decision. And we think that measuring these kinds of processes might give us some kind of insight into how people who are currently experiencing, say, hallucinations or delusions might have differences in the way that they integrate external sensory evidence with their own current model of the world. And so to start to test this, we're about to run an experimental medicine study supported by the BRC, together with our collaborators over at NPCN, in which we collect an EEG dataset on this task during administration of the NMDA receptor antagonist ketamine in healthy volunteers. And this links back to the role for NMDA receptors in psychosis that Belinda has already discussed. Okay, so I think that's potentially quite interesting. But as I mentioned at the start, I also think that there's a potential problem. And the problem is this. So every student who arrives in my lab to do an EEG experiment is handed a copy of this book by Steve Luck, which is called An Introduction to the Event-Related Potential. And it teaches many of the advantages of using EEG to measure event-related potentials during cognitive tasks. But it also has this warning in the first chapter, that event-related potentials are typically quite weak, and so you have to take lots of averages in order to measure them reliably, in order to average out the noise and recover the signal. And so this means that the average experiment needs to take at least 3 hours per participant, according to Luck. So as he points out, this kind of places significant limitations on the types of question that we might be able to answer. You know, kind of 3 hours of staring at random moving dots is kind of exhausting, even if you're an eager Oxford undergraduate. So just imagine kind of asking that of someone who's currently experiencing mental health difficulties. In addition to this, what's typically done in these EEG studies is that we're measuring these responses, and we're typically looking at them at the group average level. And what we'd really like to be able to do for psychiatry is to try and measure them at the individual subject level. But I think that there might be a potential solution to this problem. So it's true that many EEG experiments do last for at least 3 hours or more. But actually, most of the data in these experiments is thrown away before any analysis has been run on the data. In other words, most of the data in EEG experiments is what I call dead time. So what I mean by this is that although we might collect 3 hours worth of data, we're normally only interested in a very small portion of that data which occurs during the trials, during the decisions. Most of the data that we collect is actually the time between these trials. So for instance, if you're mostly interested in measuring the response that occurs kind of 300 milliseconds after the stimulus occurs, and your average trial lasts 2 seconds with a 1 second inter-trial interval, then you might collect an hour's worth of data, but you end up only using 6 minutes of that data in your final analysis. So I think what we might need to do is to try to redesign our experiments to get rid of those trials and actually try to make use of all of the data that we collect when estimating our signal of interest. And the way that we can maybe do this is by making it so that subjects don't have to solve a trial-based decision, but instead they have to perform a continuous decision-making task. And this is the work of Maria Rusler in my lab. So in the context of this dot motion task, what Maria asks her participants to do is to view a stream of moving dots, but she doesn't tell subjects when they're going to be moving coherently in one direction or another. Instead, they just have to report the time at which they think that they might be starting to move consistently to the left or consistently to the right. And what this means is that their job now is to continuously pay attention to this stimulus for a few minutes at a time, and try to work out whether or not now is the right time to respond. So they're continuously having to perform this process of evidence integration. And what Maria then does is she actually controls the exact amount of dots that move left or right on every individual frame. And this means that what she can do is she can use this alongside the simultaneously recorded EEG data to measure the influence of each of these small changes on the EEG signal. So in other words, she now makes use of every sample of EEG data to estimate how subjects are integrating this sensory evidence. Okay, so I said this talk was going to be light on data. So this is my one data slide. We've just started collecting and analysing this data, so we've only got results from the first 6 subjects. But what we can see in all of the subjects that Maria has collected thus far is that we see really clean and reproducible estimates of this decision signal at a single subject level. And while this is all still using 2 hours worth of data per subject, what Maria has found is if we split these responses up into individual 10-minute blocks, we see that there's really quite clear reproducibility of this decision signal across each of these individual blocks. So we think that this now provides us with a way to reliably measure neural signatures of this cognitive process of evidence integration using only 10 minutes of data, And so what Leila Spar, another PhD student in my lab, is going to follow us up with is by trying to study how administration of ketamine affects this signal by measuring the signal before, during, and after administration of the drug. Okay, so just to summarize what I've tried to tell you today, so I've tried to highlight that the cognitive neuroscience of decision making might have some tasks that are of relevance and importance to psychiatry. But I've also tried to argue that in order to make our experiments more clinically relevant, we need to be able to do them in shorter time frames, and that means, I think, eliminating dead time in our experiments. What we found, or what Maria's found, is that by making this task continuous, we can recover single subject markers of this process of decision formation at clinically relevant time scales. And so I'd just like to finish by thanking my funding agencies, Welcome, the Royal Society and NARSAD, thanking members of my lab, particularly Maria, who's contributed to this work, and thanking you for your attention.
Brilliant, Aaron. Thank you very much. Very exciting potential for the future. Okay, the time has come to get all of this morning's speakers back on the stage for a panel meeting. I've been watching Twitter and the questions have not been flooding in. So I'm hoping that means that you're all not tweeters and that you are going to putting your hands up in droves. I think we've got a couple of people with microphones. So, who would like to start? Great. Oh, I can see hands. It's Amy, right here.
Hi, my name's Amy. I had a question really for Lawrence, inspired by the talk we just heard. Really very interesting, and the potential solution that you have to eliminating dead time seems very elegant. And I was just curious really to ask you why we haven't had this idea before, and there's some interesting possible answers to that really. There can be inertia sometimes in the way that we work, and maybe it's that, or is there something like more computational power, or is there something interdisciplinary that led to this? Tell me more.
Thanks for the question. So I mean, I think that there are other experiments that do look at continuous event-related potentials. So steady-state visual event potentials, for instance, have done that for quite a while. Resting state analyses, but all which does make use of all of the data in estimating resting state networks. I think that the key thing that's kind of hidden in that design is the way that we analyze the data. So we're not doing what classical event-related analyses do. We're not doing event-related averaging anymore. We're having to use a convolutional general linear model in order to estimate the relationship between the signal and the changes in the decision task. That's also required us to think quite carefully about how we design the structure of that stimulus, so making sure that it doesn't change at regular intervals, it changes at kind of unpredictable intervals, designing the task so that it's kind of continuous. So I guess there's kind of a number of things, but I guess the key thing is maybe that the analytical approach is actually quite new for that analysis.
Great. Paul.
Thanks. Guy mentioned the kind of increasing challenge to research that is posed by governance issues and bureaucracy. I wanted to ask Guy, and indeed the whole panel, if they could remove or change one aspect of our current regulatory framework that facilitates our research, what would they kick out first?
Well, actually, I wrote to the Academy of Medical Sciences when they were allegedly going to reform the ethics process, probably 15 years ago. And I said they should actually abolish all of it and simply have people declare their protocols online, and that put things in the public domain, and that should be sufficient, and we should trust people to do the right thing, because they were essentially doing it in public. It'd save quite a lot of money.
I suppose I tend to be too nostalgic, but I'd like to go back to the old clinical trial system where you just have a CTX and do a study without going through the various medical directives which we have now.
I suppose it's similar. I'd like to have an assumption that clinical research is a benefit rather than the other way around. That there's no stratification, there's no different tiers of application. Everything seems to take a year, basically.
I'm also advocating removing bureaucracy, particularly for basic cognitive neuroscience studies, which don't involve any kind of experimental medicine intervention or anything like that. I mean, I come from a department in London where the ethics approval is kind of giving a 20-minute project presentation that's approved by PIs, and that kind of produces a complete shift in how willing you are to just start a study spontaneously. So that will make a big difference for psychology, I think.
Yeah, no, I agree. I suppose just as a general point, reducing the amount of paperwork, the amount of checklists, the amount of signatures for every non-substantial change would make a big difference just in the amount of staff level that needs to go into running these projects. And sometimes you feel that the paperwork is so vast that actually you could be so focused on that you don't notice things that are really clear in front of you. And those are the things that you need to be flexible enough to notice and respond to. So just simplifying everything, all of the having procedures that we all do our best practice, but with thought to how to produce that at every single stage, I think will make a real difference.
I think it's really great that also psychiatrists got an ethicist in the department, and it should be a living debate, but also the ethics of not doing research because of these procedures should also be looked at.
Right.
Thanks. Great talk. I've got a question for Guy. Really interesting talk about and sort of framing the impact of psychedelic research. And I guess I've never understood with it is it kind of gives us insight, particularly about 5-HT2A, because a lot of these drugs are partial agonists at 5-HT2A. But what I don't understand is why SSRIs don't make us hallucinate. Because isn't that what you'd expect from that, given that the serotonin is an agonist as well?
Well, I assume, I don't actually, no, I'm not up to date. I'm not up to date with the latest sort of molecular pharmacology on the conformational changes you get in the 5-HT2A receptor. But you can clearly imagine that there might be the potential for a very potent agonism, which is much greater than the agonism you get from the endogenous receptor. So I would assume that would be the explanation. I don't know that to be true. Phil, you're probably more up to date than that.
No, I think I agree with that. There's also the thought that some of the 5-HT2A receptors are extrasynaptic, so they don't normally see neurotransmitters except under extreme circumstances, like the end of a 2-day department celebration.
Thank you.
We've got one down here.
Hi, thank you very much to all the panelists for this very interesting talks. One thing that I was wondering about, we've heard a lot today about the different effects of different treatments or different levels of descriptions. And I was wondering, is there a specific level of description, either the molecular or cellular or up to the cognitive, that you think has most potential in terms of translatability in clinical practice?
Well, I mean, I don't know whether I'd say it has the most potential, but I feel like the thing, as an outsider of psychiatry, that I think is missing is that we have a really clear understanding of how drugs act at the cellular and synaptic level, and we have a very clear understanding of how those drugs produce changes in behavior, but we don't really, for almost any of those drugs, have a good systems or cognitive neuroscience explanation of that bridges across those scales. I mean, we start to see some of that from CAS work and from stories of say, reward prediction and processing in the dopaminergic mid-brain, but I think we're only at the really early days of that, and so I'd like to think that there's some potential for future work there.
I think it's a great question. Maybe we need to look at the question all the way around and look at how to go between levels rather than pitch one level against each other. Because actually the really interesting thing is how do we ask the questions that are going to make a difference in the end of the day for patients? It doesn't matter what level it is, what matters is there a mechanism? Is there something causal? Can it be modified? Is it a benefit? So that could be any level at all. And maybe we need to bring in more subjects like maths to go between those levels.
Great. I'll come to you in a second. I want to ask a question, and this one's really for Belinda. I mean, from where I'm sitting, the sort of work that you're doing, Belinda, seems completely paradigm shifting. You've identified a proportion of patients who have an organic cause for their psychiatric disease, and you're able to fix them. That's something that we've been dreaming of, right? So, is it only ever going to be a proportion of patients that we can do that for, or is it just a matter of finding more of those magic autoimmune, whatever they are?
Well, I don't think it's that rather depressing. I don't think it's that paradigm shifting. I think actually it's been hiding there in plain sight all along. I think actually the separation of our specialties between psychiatry and neurology means that we've missed it. I think the way that we view psychiatric disorders has actually been at a disservice of the discovery of causes of a proportion of illness. Of course, it's not going to be everybody with schizophrenia, but I think it's going to be a chunk, and I think we desperately need to pursue that for the potential benefit for those people.
But is it ever going to go beyond schizophrenia? I mean, is it going to be that we find a chunk of people with mood disorder, or a chunk of people with other disorders that also come into that category?
Yes, so there's a lot of interest in the possible sort of immune basis or inflammation as a causal role. In fact, a publication this morning in Molecular Psychiatry showing that cytokines are possibly causally related to depression, to the onset of depression. So that's a whole another story, really, that again is quite an exciting time for academic psychiatry, really, to sort of pursue a whole new field.
Thanks. There's one up here, and then I'll come to
Yes, my question is to Guy and to Kathy. I was really fascinated with that, this bias mechanism for how the SSRIs work. And also, Guy was talking about the lithium and the inositol phosphate pathway, and then ketamine works within a few hours. So what I was really thinking is, do all these antidepressants, are they going to turn out to have different pathways, or is there going to be some common pathway?
Yes, fantastic question, thank you. So, you're right, drugs like ketamine and other fast-acting antidepressants, as the name implies, do start to have their effects very, very quickly over a number of hours rather than weeks. So it does challenge this idea that all treatments for depression necessarily have to change how we're dealing with information, and then that will then, over time, over an inevitable period of learning, will lead to changes in mood. There's some data from animal models of depression which suggests, much like in the human case, that SSRIs affect how you deal with new information coming forward, so they allow you to pick up more positive cues as they come in. But drugs like ketamine particularly affect your retrieval of old negative memories. And so it could still be within a cognitive framework, it could still focus on cognitive bias, but it suggests that rather than needing new information to come in to test your hypotheses and to learn from those and that to be translated into improved mood, you could work backwards in what you already have in your experience and just take off some of the negative elements of memories that are already encoded. So that's one hypothesis from animal work that we've just received some funding from the MRC to directly test out in humans. But it may be that drugs don't necessarily all work in the same way. Perhaps we do need to think about other ways, and there may be different ways of interfacing with cognition in order to produce the kinds of benefits that are needed.
I I can't contribute to I think that's a great summary of the mechanistic question. There is a practical clinical question, which is that in the past we've had medications that took a long time to work. So the challenge was how long you wait before you make a switch. In practical terms, that was always a delay. It was complicated treatment. The newer treatments, which are focused on NMDA receptors or indeed GABA receptors, seem to work very quickly, as you indicated. So the problem with them is that we don't know when the patient's going to relapse. So we've kind of shifted the balance of the clinical management to kind of from the front end to the back end. And it really will emphasize, I think, the need to make measurements in psychiatry, because for too long psychiatry has not made measurements. And you know, you can't manage people's blood pressure without measuring it, and it's pretty difficult to see how you do a good job if you're not measuring the outcomes of your treatments of mood or anxiety disorder. So what's going to be required is a change in management and emphasis on, particularly, I think, gathering subjectively recorded data, or anything else, particularly objective, if you could get it, but that's much more difficult. So I see it more as a clinical interest, because the mechanistic questions are too complicated for me, but they're very interesting.
Great, and last one, Andre.
Thanks, Claire. So I've got a question from Twitter. Don't worry. Upbeat Lincoln, and they're a mental health group for people with personality disorders. I think they've seen the news from the States. They're asking about nasal ketamine spray and when it's going to be prescribed in the UK for treatment-resistant depression. They're also asking how it works, but that might be a bit too detailed a question without Rupert here.
We don't know, actually, because it's been submitted, it's been approved in the United States as ketamine, the nasal spray, so we know it's going to be available there. The European authorities have a slightly different approach to registration of particularly drugs regarding maintenance of effect, and I have no idea how they're going to treat the ketamine, S-ketamine data. So I think predicting when it will be available in Europe is really difficult. But Phil, you may know better what the background data will look like.
No, I'd agree with that, and I think that there was a good discussion of the difference in the possible mechanism by Catherine just now, and I certainly agree with that.
Thank you.
Okay, that brings us neatly to lunchtime. So I'd just like to say a massive thanks to all of the speakers this morning.